We worked out the non-relativistic Lagrangian for interacting spin-zero boson with a contact interaction, and what we found was a Schrödinger Lagrangian with a phi-4 term. This, in principle, is all we need to describe the physics of our system. And if we don't do anything to the system, it is likely to be found in its ground state. So that's an eigenstate of the Hamiltonian, and therefore what matters here is to work out the energy for the system, and given by the Hamiltonian as a conserved quantity according to Noether's theorem. The same Hamiltonian is also what we need to predict the future of the system, how it is going to evolve in time. So we will work out Hamiltonian in the framework of canonical quantization. In the relativistic case, the field operator was a solution of the Klein-Gordon equation. The first part deals with particles and the second part with antiparticles. But we already know that in the non-relativistic limit we won't have antiparticles, so we can get rid of this part. And also in the non-relativistic limit, k squared is much smaller than m squared, and therefore omega k can be approximated by m. And recall that we defined the slowly moving phi from the relativistic field. So we get our expression for the non-relativistic field. We end up with a field which has no time dependence in it, and that's because we made this drastic approximation that omega k is just m. In fact, if we take Taylor expansion, we will still have some momentum dependence, and that will leave some time dependence in the field. But for simplicity, let's just assume a static operator. And to canonical quantize, we also need to work out what is the expression for the canonical momentum pi. We can now replace pi by I phi dagger in the expression for the commutator. We see that if we set the commutator between A and A dagger to be a delta function, we get the desired expression for our commutator. When we deal with a many-body system, it's usually limited in space, in a given volume V. This means that the integral over momentum can be replaced by discrete sums. The expression for the non-relativistic field then involves this discrete sum over the momentum. The 1 over square root of the volume is required by dimensional analysis. Indeed, from the Klein-Gordon Lagrangian, we can see that the relativistic field has a dimension of an energy, and therefore the non-relativistic field, because of the 1 over square root of m, has a dimension of an energy 3/2. From the expression for the non-relativistic field, we see that A of k has a dimension of an energy minus 3/2. But now it is turned into an operator which has no dimension. So the only way we can recover the dimension of an energy 3/2 for the field is by dividing by square root of v.